All right, electric potential energy is very similar to our calculations for the potential. So as we said before, the potential at point P due to this charge Q1 is going to be K Q1 over R, and that's how we find the potential. Now, the work required to bring another charge, Q2 from infinity, so let's say that I have Q2, it's way over here, and I want to bring it to this point P, to this point. And I want to know how much work is required to bring that charge into that point P. Because notice, as I bring this charge in, it's going to experience forces that will either cause me to do more work or actually cause me to do negative work, depending upon the direction of the forces. I want to know how much energy is required or how much work is required in order to move this charge from here to here. And then that will tell me how much potential energy I have within the configuration of charges. The amount of work that I do will equal the potential energy. All right? So my change in potential energy is going to be equal to Q2 times V1. And this goes back to our definition for voltage, that potential is energy over charge. And you can see here that this is that same expression, just written a little bit differently in terms of energy as charge times our voltage. So if I want to know what is my potential, it's going to be, or my potential energy gain, it's going to be Q2 times V1. Remember, V1 was KQ1 over R. That's that point P. That is the potential at this point P where I'm moving that charge. And then, so I can find my delta PE is going to be KQ1 Q2 over R. That's our expression for potential energy. But really, in order to do this, we'll have to work through some examples. I'm not sure if I have an example here. Okay, I'm going to go over this. If this is useful for you, then that's okay. If it's not, then please just discard it. So if Q1 and Q2 are both positive, then we find then that the potential energy contained here, PE, which as we derived before is KQ1 Q2 over R, and we find that the potential energy is positive. All right, that means that positive work must be done to hold them in place because the force and the displacement are in the same direction. So I'm applying a force in this direction, which would tend towards a displacement in that direction. So that's going to be positive work. Similarly, if Q1 and Q2 are opposite in charge, then the potential energy is negative. That means that negative work must be done to hold them in place. So I have to have a force acting in this direction in order to keep them from colliding together because they're attracted to one another, with a tendency for the displacement to go in this direction. Right? They're moving in together towards that direction. I'm not sure if that really helps you. If it doesn't, then please just, forget that I ever said that. But let's work through a problem right here. I have two charges in this figure separated by 1 meter. How much work is required to assemble the charges? Well, this one's pretty simple, and then I'll add a third charge. All right, actually, I'm going to go ahead and add a third charge here. Well, no, I'll do this the easy way first. So the potential energy is going to be, let's call this Q1, and I'll call this Q2. I'm going to go a little bit roundabout way here. I'm going to say that the voltage due to charge 1 is going to equal KQ1 over R. All right, and I'll go ahead and calculate this. 9 times 10 to the 9. Q1 is 2 times 10 to the minus 6 coulombs divided by 1 meter. All right, so let's see. That is 18 times 10 to the third. So that voltage is equal to 180 volts, that potential. So the point here is 180 volts due to this charge. And then my potential energy is going to be Q2 times the change in potential for Q2. And so that's going to be, let's see, what is this charge? negative 3 microcoulombs, or negative 3 times 10 to the minus 6 coulombs, times 180 volts. And that's 0.005 times 10 to the minus 4. Negative 5 times 10 to the minus 4 joules. That is the potential energy contained here. Those have positive and negative charges, so I'm going to have a negative potential energy because I have to do negative work to hold them together. Here, I'm going to give you this quick test. I'm just going to work through it here. It's a good example. Actually, let's go to the end of your textbook. Oh, let's see. I don't have that, but you have them in your in the back of your book. So if you go to the back of your book, you can find the old exams. I'm going to go here, look at the old exams, and we'll work through a problem that has 3 charges, because that's more like what you'll see. Okay, 2 charges are arranged on the vertices of the equilateral triangle shown in the previous figure. If Q equals 2 microcoulombs, how much work would it be to bring a charge of value Q from a very large distance away to the top of the triangle? Alright. Let's first work number 14. So I want to know what is the So first we just want to find what is the potential. I'm going to look at this question. I have 10 microcoulombs here, and I have negative 6 microcoulombs here. And I want to know what is the potential up here. So that potential is going to be the sum of the individual potentials, which is going to be KQ over R. It's 9 times 10 to the 9, times 10 times 10 to the minus 6. That's coulombs, divided by 1 meter, plus 9 times 10 to the 9, times 6 times 10 to the minus 6. This is a negative value, because it's a negative charge, divided by 1 meter. This is just like we did before, finding the total potential due to these collection of charges. Oh, this should be a positive 9 right here. And I get 36,000 volts. Now, in this next question, it's asking us how much work is required to bring a charge of 2 microcoulombs and put it at the top here. All right, my work is equal to Q times delta V. Okay. So my work then would equal to 2 microcoulombs times the change in potential for that charge, and that change in potential is going to be 36,000 volts. That's 2 times 10 to the minus 6. It's 36,000. That's 72,000 times 10 to the minus 6. 0.072 joules. So that's the amount of work required to bring that charge and place it at that topmost place. Now let's say that instead I wanted to assemble all 3 charges. So I have 2, 10, and minus 6. So this is separate from 15, but this is an example like it's in your quick test. Let's say that I had 2 microcoulombs, 10 microcoulombs, and negative 6 microcoulombs. I want to assemble these charges, and they're all 1 meter apart. So this distance is 1 meter, 1 meter, and 1 meter. The way I do this is I bring all 3 charges in. Now I imagine that I'm just bringing the 2 microcoulomb charge, for example. So here, actually let's do the 10 first. I bring in the 10 microcoulomb charge, and I ask myself how much work was done to bring that charge into place. Alright, the work required to bring it into place for the 10 microcoulomb charge, there are no other charges there acting upon it, so that work is equal to 0. Then I bring in the negative 6 microcoulomb charge. And I want to know how much work is required to bring it into place. And that's going to equal to Q times delta V. Q is going to be this charge times the potential due to this charge at this point. So that's going to look like this. It'll be negative 6 times 10 to the minus 6 times K, 9 times 10 to the 9th, Q, which is going to be 10 times 10 to the minus 6, divided by 1 meter. And that's going to be the work required to bring in that negative 6 microcoulomb charge. So that's going to be 0.54, negative 0.54 joules. So far I have 0 joules, 0.54, negative 0.54 joules. And then I want to know how much to bring this 2 microcoulomb charge into place. Look, I've already figured that out. That was up here. That is this 0.072 joules. So 0.072 joules. So my total energy that's contained within this whole collection of charges, my total energy is going to equal negative 0.54 plus 0 plus 0.072. And that's equal to 0.498. We'll just call it 0.5. Negative 0.5 joules. And so that's the total potential energy. Now, this might not make sense to you just yet. There are some homework problems that would be useful for you to look at, and then there are also some other old test questions that actually have 3 charges like this for you to look at. And I'd recommend that you do that. If it's still not really making sense, then you should really come see me. You can also find this in any of the online textbooks, the OpenStax books, or any of the ones on the website. So please come see me if you're having trouble with this.